Hello students, welcome to All Force e-learning program. Today now in this session we shall learn about electric lines of force and their properties. Electric lines of force and their properties. So before just have a glance over the things what we have learned. So I was telling you charge is a fundamental property, right? Charges experience force, Coulomb's force as stated by Coulomb, force directly proportional to product of the charges, inversely proportional to square of distance, F is K, Q1, Q2 by R square, right? And the impact of one charge on the other is explained by field, electric field. So the field is the force experienced by a unit positive charge in the electric field at that point, placed at that point. Field at that point is the force experienced by a unit positive charge. Now the concept of field is explained by a thing called electric line of force. What are electric lines of forces? Let's understand. Now the idea of electric lines of forces was proposed by Mr. Michael Faraday. Right? Michael Faraday said that lines of force would give you the correct visualization of the electric field around the charge. It gives the clear picture of the field, the orientation of the field, right, due to the charge that is being produced. It was a very good idea using which, right, we can explain the field pattern. First, what is an electric line of force? Electric lines of force, please understand, electric lines of force do not exist physically. Physically they have got no existence, they have got no significance. They are imaginary lines, right? They are imagined. That how does the field show the impact? It shows the visualization. They are geometrical constructions which show the pattern of the electric field, the orientation of the electric field, but they are not really existing phenomena. So sometimes in a previous question, sometimes he was asked, they exist from moving from positive to negative charge. They do not exist. They are imagined to go from positive to negative charge. They have no physical existence. So what are lines of force? The imaginary line or curve drawn in the path, in the direction in which a unit positive charge would tend to move in the field. They are imaginary lines actually. Suppose if I consider a positive charge, the imaginary line in which, or a curve, it can be a curve even, the line in which a unit positive charge would tend to move, right, it would tend to move in that field. And suppose if there is a curve like this, imagine, suppose, then the path in which the unit positive charge would tend to move, the curve in which the unit positive charge tend to move is termed as line of force. And at any point, the tangent drawn at that point gives the direction of the electric field at that point. The tangent drawn to that curve, the tangent drawn to the electric line of force gives the direction of the electric field at that point. Right? Suppose if it is this point, at point A, the direction of the electric field is EA. At point B, the direction of electric field EB. At point C, this way. Tangent drawn to the curve will give the direction of the electric field at that point, right? So the electric lines of force are imaginary lines, right? They are imaginary lines, geometric constructions, lines or curves. So the imaginary lines or curves drawn in the direction, in the path in which a unit positive charge would tend to move in the field. And the tangent drawn to that at any point, the tangent drawn at any point to that curve shows the direction of the electric field at that point. Right? This is electric line of force. The concept of electric lines of force actually simplifies the study of electric field. Right? It simplifies the study of electric field. Now, how does these lines of force exist? The different patterns of electric field, electric lines of force are given like this. First one, different patterns. A. If the lines of force are parallel and equidistant, the lines of force are parallel and equidistant, then it implies the magnitude of the electric field is constant and the direction of the electric field is also constant. That means this represents uniform electric field. This is the pattern of the electric lines of force for uniform electric field. I was telling you the example. The example for uniform electric field is the electric field between uniformly charged capacitor plates. Uniformly charged capacitor plate, the lines of force would exist like this, right? They are uniform. Magnitude is always constant at all the points and the direction is same. They are parallel lines. Uniform electric field it is. Second one, now the direction is same but the magnitude is different. You see here the lines of force are far apart but here more crowded. In this one the magnitude is different but the direction is same, right? Whenever you find the lines of force pattern in such form where at one place the lines of force are more crowded, other place where they are spaced apart, then this represents the electric field where the direction is same but the magnitude is different, non-uniform electric field. Now third, the lines of force are curved like this but spaced at equal distance. They are spaced equidistant apart but the direction is different. So direction is changing from point to point. In this one magnitude is same but the direction is different. Magnitude same because they are equidistant, they are separated by equal distance apart but the direction is different. And finally the fourth one, if the magnitude and the direction is changing like this, diverging field, now they are crowded more here, field is more, they are far apart, field less, and the direction is also changing. Here it is a pure non-uniform electric field where the magnitude and direction is changing continuously from point to point. So these are the different patterns, right? First, uniform electric field, magnitude, direction both constant. Direction is same but magnitude is different. Here magnitude is same but direction is different. Direction is changing, curved, the direction is changing like this. Here both magnitude and direction both are changing continuously from point to point. Right? These are the first patterns. Next, suppose if I consider a positive charge, what would be the pattern? If I consider a positive charge, then the lines of force are like this. For a positive, isolated positive charge, exclusive positive charge, lines of force are like this. So, lines of force diverge away from the positive charge. They are moving away from the positive charge like this. But as they move away, as they move far, they are getting diverged like this. Diverging field. If I consider exclusive negative charge, only negative charge, isolated negative charge, then the electric lines of force converge to the negative charge. They are moving towards, they converge to the negative charge. Isolated negative charge would have electric lines of force like this. For positive charges, they diverge away. For negative charges, they converge towards one another like this. Let's continue. Let's take up the electrical lines of force pattern. The pattern of the electric field for two equal and identical charges, plus Q and plus Q. Identical point charges, equal and identical point charges separated by a distance like this. Now, since the magnitude is same, the number of lines of force emerging from a charge purely depends on the magnitude of the charge. In fact, the number of lines of force are directly proportional to the charge. The number of lines of force enclosed in a boundary, number of lines of force, the net lines of force are directly proportional to the charge, the magnitude of the charge inside. This is actually Gauss law. We will be learning about it in the later classes, this thing. So number purely depends upon the magnitude of the charge. Then since the magnitude of the charge are same, the number of lines of force emerging from this and the number of lines of force emerging from this will be the same. Now, one here, same identical here, another one here and here, same identical here and here, right? Then line of force here and here, like this. Let's suppose here also lines of force like this and this way. Okay, let's take some more. Now a line of force like this, a line of force like this. Similarly here also this way, and right, This way it is, lines of force. So the number of lines of force emerging from the first one and the number of lines of force emerging from the second, both are same. So the number of lines of force are same. So this is the pattern for the electric field, or the pattern of the electric lines of force for two identical like charges, plus q plus q. Since the magnitude of the charge is same, the number of lines of force emerging from this is same as the number of lines of force emerging from this. And since they are like charges, the lines of force, in case of unlike charges, we have observed the lines of force getting they are getting combined, but here they move away, they repel, they diverge, they move away, they don't touch each other. They all move away like this and they all go to infinity. All the lines of force nowhere in the vicinity, nowhere around, they touch one another. They all move to infinity. Now you get a doubt. What does, when I consider these two charges, now what happens to the space here? In this space there are no lines of force, right? This space is empty. Now why the space there is empty? Now actually what happens is the lines of force coming from this positive charge and the lines of force coming from this positive charge interact. But since they are of same nature, they diverge away. They move away like this. They move away from one another, right? They move away from one another, repelling one another like this. Repelling one another like this, move to infinity, producing a space between them with no lines of force. And this point is called as null point. Now, no field point, null point. No field point is a point where there is no electric field, and there is no electric field even around in its vicinity. Around the charge also there are no lines of force, no electric field. So there is no question of the field there. But at this point, it is something different. There is electric field around at all the points in the vicinity. There are electric lines of force existing around its vicinity, but there is no electric field at that point. The point in the electric field, so this is a space where the electric field is existing, but in the space there is exclusively a point where the resultant electric field intensity is 0. So this point is termed as null point or neutral point. Since both the charges are equal in magnitude and like charges, null point is produced exactly at the midpoint between them. The pattern of the lines of force is symmetrical, identical about this axis. Symmetrical pattern of lines of force are produced at the null point at this point. This is the pattern for the electric lines of force, two equal and opposite charges. Next, suppose if I consider capacitor plates, a uniformly charged capacitor plates, conducting plates, the charge is the plate is uniformly charged here. Right here it is minus q, right? It's plus q and minus q, two equal and opposite. They are two equal and opposite charges, but not point charges. Earlier we have taken two equal and opposite point charges, for which the pattern was for two equal and opposite point charges. The pattern was the lines of force were converging, meeting one another, and they were extending like this, right? But for this capacitor plates, the pattern, the lines of force are parallel lines. The lines of force are parallel lines and uniform. The lines of force are parallel and equidistant, separated by equal distance. Uniform electric field is produced. A uniform electric field will be produced. The pattern of the electric field is like this. So parallel and equidistant. But to be very specific, when you are very keen, then actually at the edges we find a small fringing. At the edges we find a small pattern where the lines of force get curved, called fringing of the electric field. But this is negligible if the distance between the plates is small. If the distance is small, plates are very close to one another, this fringing is also negligible. A uniform electric field will be produced. So for a capacitor plates, uniformly charged capacitor plates, the pattern of the electric lines of force are like this. Suppose if there is a plate, if there is a capacitor plate positive and a point charge, a capacitor plate and a positive charge, or a point charge is placed near to the point charge a conducting plate is placed. Suppose if I consider a point charge like this and a conducting plate is placed nearer to it, then the pattern of the electric lines of force is like this. The pattern of the electric lines of force would be this way. The lines of force emerge from the positive charge and they end up at the surface of the conductor, right? Surface of the conductor like this. This way you get the charge. For a conducting plate, when a conducting plate is placed near the charge, charge is actually induced on it. Positive is induced this side, negative that side. For between them, the lines of force pattern will be like this. So this way, the electric lines of force, different patterns of electric lines of force are denoted like this. Now, coming to the properties of electric lines of force, if we talk about the various properties of electric lines of forces. Now, so next, the properties of electric lines of force. Now, first point, electric lines of force are imaginary lines. So I was telling you, they are not physically existing lines. They do not exist physically. They are imaginary lines or imaginary curves drawn, which are the geometrical constructions actually, which show by which we can visualize the pattern of the electric field. So they are imaginary lines. They are not really existing. They have no physical existence. Imaginary lines are curves which are geometric patterns by which we can visualize the pattern of the electric field there. Second, electric lines of force, they originate from the positive charge. They come out from the positive charge and they end up at the negative charge. They start from the positive and they end up at the negative charge like this. They diverge from the positive charge and they converge to the negative charge. From the positive charge, they move away apart. They diverge. To the negative charge, they converge. They come closer, right? So, from the positive charge, they diverge, move apart. Start here, end up here. So, electric lines of force are not closed loops. They are open lines. They start here, they end up here. Unlike magnetic lines of force, they are closed loops. Magnetic lines of force are closed loop. They do not have starting and ending point. But electric lines of force, they start from the surface and end up at like this. They diverge from the positive charge, they converge to negative charge. They start here, they end up here. They are open lines, not closed loops. But magnetic lines of force are closed loops. They do not have starting and ending point there, right? Third point, electric lines of force. Now these electric lines of force, they do not pass through a conductor. If I consider a conductor, positive, negative, then lines of force end up, if it is positive, they emerge from the positive charge. From the surface of the positive charge, they emerge. If it is negative, they end up at the negative charge like this. But they do not pass through the conductor. Electrical lines of force do not pass through a conductor. But magnetic lines of force pass through the magnet. Unlike electric, magnetic lines of force, they pass through the magnet. They emerge from the north pole. They curve out like this and they enter at the south pole. They are closed loops, but they are not closed loop. They start at the positive, end up at the negative like this, right? And they never pass through the conductor. Through the conductor, the lines of force zero, because the electric field inside the conductor is zero, right? We will be learning in the later classes. There is no electric field inside the conductor, so lines of force never pass through the conductor, right? They are open lines. And even electric lines of force, they emerge or they enter, they emerge or they end up normal to the surface of a conductor. For a conductor, electric lines of force always emerge or they end up normally at the surface of the conductor like this. they emerge normally, perpendicularly like this. Now based on this, there was a beautiful question asked in one of the entrance examination. There is an electric field produced by a capacitor plates, uniform electric field. So the lines of force are like this, plus to minus. The lines of force moving from plus to minus. Now in this, a conductor, a spherical conductor is placed in this electric field. Between the plates of a capacitor, a uniform electric field is produced. So this is positive and this is negative. So the lines of force move like this. The lines of force are like this. Now in between them, a neutral conductor is placed. Then the question is, what would be the pattern of the line of force in this conductor? He had given 4 different options. One of the options saying that it goes inside. One of the options saying that they diverge away. One of the options say that they go like this, they end up and they start here. One of the things saying that they end up here and again they continue like this. And the actual answer is, line of force come like this and they end up normally to the surface. Similarly, they emerge normally and go like this. So this is the correct answer. First thing, lines of force never pass through a conductor. This is not correct. Right? Lines of force are not induced. Charge is induced. So lines of force, conductor receives charge. So lines of, they do not diverge away from the conductor. And lines of force, they end up, but they do not touch at any angle. Here you see the tangent makes an angle, some angle. So the actual thing is, line of force end up or emerge from the surface. They do not pass through the conductor, and at the conductor surface they end up normally or emerge normally like this. This is the correct option. A very beautiful question. In the entrance examination, such type of typical things, tiny things, you have to be very keen about such tiny points. That is the reason why we are going in exclusive manner, right? Giving you every tiny bit so that you may not lose the fund. These are basic fundamental things which you have to keep in mind there. Okay. So lines of force for a conductor, they emerge. Either they emerge or they end up at the surface of the conductor. They do not pass through the conductor, and they always end up or emerge normal to the surface of the conductor. There is an exclusive reason for this, why they emerge or end up perpendicular, normal to the surface. We will be learning in the next chapter, right? So next, electric lines of force are open lines. They are not closed lines. This is a perfect proof that to show that electric field is a conservative field. The work done in a closed path is zero. They are conservative. To prove that it is conservative, it is confirmed that the lines of force are open lines. They are not closed lines. Right? Lines of force, that they are conservative. The electric field is a conservative field. Work done in a closed path is zero. To prove it, we say that the lines of force are open lines. Lines of force, they emerge. They emerge. They are not closed lines. They do not end up at the same charge. For the same charge, they cannot emerge and end up at the same charge. So they are not closed loop. They are open. They emerge from one charge, they end up at the other charge, or they extend up to infinity, but they do not end up start from the same and end up at the same. They cannot go along the same line and again come back. So they are not closed loops. Next, the most important is, when I consider a charge, right, at any point the tangent drawn to the line of force, the tangent drawn to the line of force always gives the direction of the electric field. The tangent at that point gives the direction of the electric field like this, right? So therefore, right, the tangent at this point, direction there. That is the reason why there is a very important thing. Can two electric lines of force cross over one another, meet over one another? The answer is absolutely no. Because if at all, if two line of force cross over one another, then at this point, if I consider this line of force, then the tangent drawn at that point should give the direction of electric field. But if I consider this line of force, the tangent drawn at that point will give the direction of electric field. A unique electric field cannot have two different directions. The unique electric field cannot have two different directions. This is absurd, impossible. So no two lines of force will intersect, no two lines of force will cross over one another, which is impossible there. right? Tangentron. And one more important point to note, suppose if there is a electric field like this, electric field. Now if I consider a unit positive charge, then the direction in which the unit positive charge would tend to move does not clearly give you the path of the line of force, because you know this, due to this charge is accelerated, it is accelerated. So due to this, let the acceleration be like this here. Because of the acceleration, the velocity vector will lie like this, but due to the path, due to the line of force, the force vector acts this way. So velocity vector will be in this direction, acceleration vector will be in this direction. The positive charge will neither move along velocity vector nor acceleration vector, the line of force. So the path of the positive charge cannot clearly give the direction of the electric line of force. This is keenly to be understood, keen to be make a note of it. Next, lines of force, electric lines of force. If I consider positive and negative charge, longitudinally they contract, right? They are coming towards, longitudinally they try to come towards it, like a stretched string. In case like a stretched string, they try to come closer, they try to contract, but laterally they repel, they separate, transversely they separate. Longitudinally they try to contract, but transversely they separate, they move apart there, right? So this is another exclusive point which you have to remember. The number of lines of force, the measure of number of lines of force emerging from a charge is directly proportional to the magnitude of the charge. In fact, there is a law stating about the number of lines of force. The number of lines of force emerging from a enclosed this thing, right? The number of lines of force emerging is directly proportional to the charge that is enclosed inside the closed loop, right? So closed boundary. So the number is directly proportional to charge, right? Q. In fact, it is the number of lines of force emerging from a enclosed boundary is equal to Q by epsilon naught stated by Gauss. The total measure of total number of lines of force emerging from a enclosed boundary is equal to Q by epsilon naught stated by Gauss law. And even suppose if I consider suppose there is an electric field existing like this, then through a particular area, unit area, the measure of number of lines of force passing through a unit area, measure of number of lines of force. Now this is directly proportional to the electric field intensity at that area, at the point on the area. So the number of lines of force per unit area, actually number of lines of force per unit area is termed as electric flux density, right? This is proportional to the electric field at that point, right? And electric field, the strength of the electric field can be, the major use of the electric line of force is to, by visualizing the electric field pattern, we can differentiate the magnitude of the electric field at different points. Suppose if the electric field is like this, electric field is diverging like this, here the electric lines of force are more crowded, more number of lines of force per unit area. So the strength of the electric field, let us say E at electric field is more, but here the lines of force are moving apart, they are getting separate, they are spaced like this. Then the electric field at this point B is less, so EA is greater than EB. The electric field at A greater than electric field at B, right? So the major use of the lines of force is that they can be used to compare the strength of the field at two different points in the electric field like this, right? So this way you can make out the properties of electric lines of force, right? Thank you.